In today's lesson, we are going to be looking at dependent and independent events. So this is going to kind of wrap up our simple probabilities. We've already looked at theoretical versus experimental, how they differ and how they connect, and we've looked at mutually exclusive and non-mutually exclusive events. So again, the dependent and independent events, we're just going to add some complexity to that. Again, going to force us to take a little bit of a look at the actual question to figure out what are we looking at, what events are we looking at. So before we get into that, we're going to look at two different interactive scenarios. So we're going to look at, in our games fair, the 4-coin flip and the 5-card shuffler. So if we look at those two events, we're going to look at the 4-coin flip first. And while we look at these events, I want you to think about how the probabilities of each outcome in the game might be calculated. You might not know specifically how to calculate them, but just think about what are some things you need to take into consideration while calculating them. So if I look at the first one, the 4-coin toss, basically we're flipping 4 coins. Each flip costs 10 points. I win 10 points if I flip all heads, 10 points if I flip exactly 2 heads, or 30 points if I flip no heads. So again, the idea is I'm just flipping 4 coins and seeing what I get. And based on those outcomes, will I win points or will I lose points? So again, think about how could you calculate the probability of each of these outcomes. And again, if you can't actually work through and calculate it, what are some things you need to take into consideration? How are these different from the last ones? Examples that we've looked at in the past lessons. The other game that we're going to look at is the 5-card shuffler. So essentially, you are being dealt 5 cards. Each hand of 5 costs 10 points, and you win based on the number of hearts in your hand. 20 points for no hearts, 0 for 1, 10 for 2, 20 for 3, 50 for 4, or 1,000 for 5. So again, dealing the cards and seeing what our outcome is based on the number of hearts. And we want to think about how is the outcome of, or how is the probability of each outcome calculated? Right, so again, these outcomes of getting hearts, how are these outcomes calculated? What is the probability of each? How does this differ from the 4-coin toss? What are some things we need to take into account when we're looking at this game compared to the last game, and even compared to the other options that we've talked about in previous lessons? So we'll come back to these when we talk about them again, once we learn a little bit more about dependent and independent events. But looking at independent events are events where the occurrence of one event has no effect on the other event. So the events that are happening do not affect one another. The one event does not affect the outcome or the probability of another event. And if two events are independent, then probability of A and B, so this is a key thing we're going to be seeing, the probability of A and B is equal to the probability of, again, this is just another way to represent A and B. So again, this is an intersection. So A intersection B, or A and B, is equal to the probability of A times the probability of B. So this is different because we're multiplying the two events together, or the probabilities of the two events together. So let's go back and revisit some of those games and think about which one was independent. And if it's not independent, then we can reason that it's dependent, and we'll touch on what dependent is in a little bit. But if I bring up these two games, looking at the 5-card shuffler first, where we left off, does one card being dealt affect the outcome of each previous card, of each future card being dealt? So being dealt this 2 of clubs, does that affect the probability of getting the next card? If getting the 4 of diamonds affect the probability of the next card, and so on? Do they affect one another? In this case, you could say yes, they do. If I'm being dealt one card, then that changes the outcome or the probability of what my next card could be, and so on down the line for each card being dealt. So you could argue that these are not independent events. These cards are all connected, or the probability of each card being dealt is connected to the previous one. Looking at the 4-coin flip, if I'm flipping 4 coins, event A, B, C, and D would be each coin being flipped. Does the probability of each flip, or does the flipping one coin affect the probability or outcome of the other coins? Or does flipping one coin affect what I could get in the second coin? In this case, no. They do not affect one another. So in this case, looking at this game, these are independent events. Flipping 4 coins or flipping one coin does not affect the outcome or change the outcome of what I could get with the next coin. They're all separate. Even if I flipped one coin 4 times, it's still not affecting the outcome. So these are independent events. So again, the 4-coin flip was independent, the 5-card shuffler was dependent, and we'll talk a little bit more about dependent later on. So moving into some examples. Example 1, a spinner has 10 different equal size sections and a standard deck has 52 cards. You spin the spinner and draw a card. A is asking how many total ways are there to spin the spinner and draw a card, or draw the card, if you're drawing one card. And if I look at the spinner, I can count, and there are 10 different colors or 10 different slices, so 10 ways to spin. And if I look at the cards, there are 52 cards in the standard deck, so there are 10 ways to spin and 52 ways to draw, or to draw a card, because there are 52 outcomes that I could get. B is asking, what is the probability of spinning a red and drawing a 5? So the key thing here, again, we're seeing and in the question, which is different from mutually exclusive and non-mutually exclusive. So I have to think about, are these independent events? Does spinning the spinner affect or change the outcome of the card that I could draw? And in this case, no. Spinning the spinner does not affect the card that I would draw. It's 2 separate events. So what we're going to be doing here, the probability of spinning a red and drawing a 5 is going to equal the probability of spinning a red times the probability of drawing a 5. The probability of spinning a red, there's only one red here, one red slice, so 1 out of 10, times the probability of drawing a 5. If I look at my deck, I can see that there are 4 5s out of 52 total cards. So I get 4 out of 520, which can be reduced to 1 over 130, which works out to roughly 0.77%. So there's less than a 1% chance of getting, or of spinning a red and drawing a 5. Again, you could reason through that does make sense, because again, both outcomes need to occur in order for this to work. And if you think about that, there's lots of different outcomes that you could get, lots of different choices or possibilities. So it does make sense that it's a quite low probability of these two occurring back to back. Example 2. There are 2 boxes. The first contains 5 red marbles and 3 white marbles. The second contains 4 black marbles and 7 green marbles. If one marble is selected at random from each box, what is the probability that the marbles chosen will be white and black? So in this case, there's quite a lot of things going on here, a few numbers. Let's go through and read through it again, and let's underline some key things and highlight what it's asking us. So the first box contains 5 red marbles and 3 white marbles. The second box contains 4 black marbles and 7 green marbles. If 1 marble is selected from each box, what is the probability that the marbles chosen will be white and black? So I need to think about these two events. Does choosing a white marble or does choosing 1 marble from the first box affect the outcome or change the probability of me choosing a black marble from the second box? And in this case, it does not. These are 2 independent events. Me picking 1 marble from one box does not affect how I pick a marble from the second box, or it doesn't change the probability of what I could get in the second box. They're 2 separate boxes, they're independent events. So in this case, the probability of choosing a white marble and a black marble is going to equal the probability of choosing a white marble in the first box multiplied the probability of choosing a black marble in the second box. Looking at the white marble, the probability of choosing a white marble is 3 out of 8. There are 3 white marbles out of a total of 8 marbles. And I'm going to multiply that by the probability of choosing a black marble in the second box, which is 4 out of 11. There are 4 black marbles out of a total of 11 marbles. If I multiply these 2 probabilities together, 12 over 88, which can be reduced to 3 over 22, which works out to about 13.6%. So there's a 13.6% chance of selecting a white and a black marble from the 2 boxes. Example 3, the probability that Allison passes her math test is 0.9 or 90%. The probability that she passes her English test is 0.7 or 70%. What is the probability that A, she passes both, B, she passes math but fails English, and C, she fails both? So this one I'm going to get you to try on your own. So again, I'm going to suggest that you pause the video, try to solve this one on your own. Again, think about, are these independent or are they dependent events? Or maybe are they mutually exclusive and or non-mutually exclusive events? Once you figure out what event you're looking at or what type of event, you should have a formula then to use. Keeping in mind, we're already given the probabilities as decimals, so we don't have to worry about creating fractions or figuring out what's the total number of outcomes or anything like that. We're already told what the probabilities are. We just need to use that. So again, I recommend pausing the video so you can try this on your own. So coming back to this, we're going to walk through each one. And if you already know, if you can already double check your answers and kind of wait and listen to the explanation. But for A, if she passes both, so again, we should have recognized that these are independent events. So her passing math does not affect or change the outcome of her passing English. 2 separate events, they're not connected. So if she passes both, what's the probability of that occurring? In that case, because they're independent events, we're going to multiply the probability of her passing math times the probability of her passing English, which we're already given, and we get that it's 63%. So there's a 63% chance that she's going to pass both. What is the probability that she passes math but fails English? In this case, we've already reasoned that they're both independent events, they're independent events together, so we're going to multiply the 2 probabilities. We know the probability of passing math because it's given to us, but we don't know the probability of her failing English. It's not given to us, but we are given enough information to calculate it. going back to when we talked about theoretical probability in a previous lesson, we talked about the complement, which is the opposite. So the probability of her passing plus the complement, or the opposite, which in this case would be the probability of her failing, those two probabilities have to add up to equal 1. That's the most probable that you can, or most probability you can have is 1 or 100%. So in this case, the probability of her passing English, which is 70%, plus the probability of her failing needs to equal 1. You can rearrange this equation and solve and realize or determine that there's a 30% chance of her failing English. So that's the probability that I'm going to use, and I'm going to multiply in my formula. I should get that the probability of her passing math but failing English is 27%. For C, the probability that she fails both, we already know the probability of her failing English. We've calculated that for the last question. And for failing math, we can use the same reasoning and calculate that the probability of her failing math would be 0.1 or 10%. Again, I already know that these two events are independent, so I'm just going to multiply the two probabilities together, and I should get 0.03 or 3%. So there's a 3% chance that she's failing both. Moving on to a more straightforward one, what is the probability of rolling a sum of 6 with 2 dice followed by a head with the flip of a coin? So again, I don't see the word and in here. I also don't see or, so let's kind of read through and underline some things. What is the probability of rolling a sum of 6 with 2 dice, so there's one event, followed by a head with the flip of a coin? So there's the second event. So this term followed by, this is referring to and, or is another way of saying and, because we're saying event A and or followed by event B. So we have to think, are these two events linked? Are they dependent or are they independent? Does rolling 2 dice affect the outcome of flipping a coin? And in this case, they do not affect one another. So these are independent events. So if I'm looking at the probability of rolling a sum of 6 and getting a head when I flip the coin, I'm going to look at what's the probability of me rolling a sum of 6, and I'm going to multiply that with what's the probability of me getting a head when I flip the coin. If we're not too sure what the probability of getting a sum of 6 is, I can always go back to my previous note where I looked at I created the table for the sum of 2 dice. I can also bring it up here, and looking at it, we can see that the sum of 6 occurs 5 times out of 36. So 5 times out of 36 times, what's the probability of flipping a head? In this case, it's 1 out of 2, or 50%. And when I multiply my two probabilities, I get 5 over 72. It doesn't reduce to anything, but it does work out to about 6.94%. So there's a 6.94% chance of me rolling a sum of 6 and flipping a head with a coin. The next thing we're going to look at is independent events, or conditional probability. So an independent event is the opposite of a dependent event is the opposite of an independent event. You may have already guessed that, and you can probably reason through what a dependent event is. But if not, events that have different outcomes depending on what was already happened or what has already happened, and the outcome of one event depends on the other outcome of another event. So basically, these events are connected. One event depends on the other. And it's also known as conditional probability, because you might see it written as the probability of event A on the condition of event B happening, or something along those lines. So the formula that we use is exactly the same, roughly, as independent events. So if two events are independent, then the probability of A and B, again, we see and, so again, same keywords, so we're going to have to really be looking at the question to understand what it's asking us. So the probability of A and B is basically the probability of the intersection of A and B. So again, intersection, which just means and, is equal to the probability of event A times the probability of event B given that A has occurred. So what this means here with this line, this is just basically saying the probability of event B given that event A has happened. Has happened or has occurred, however you want to word it. Now you might be thinking, well, okay, this is going to get really difficult. How do I calculate the probability of something happening given that something else has happened when it's all theoretical? And for the concepts of this course, don't worry, you will be told what the probabilities are. So you'll be told that the probability of event B given event A, you'll be told that conditional probability. It may even be worded as the conditional probability. So you just have to recognize what it is that you're being asked for. So if I look at the next question, if the Montreal Canadiens have a 80% chance of winning at home and a 60% chance of winning on the road, what is the probability that they win any random game in the season if a random game has a 70% chance of being a home game and a 30% chance of being a road game? So essentially saying that there's 10 games left, 7 at home, 3 on the road. So again, there's a lot to unpack in this question because there's a lot of information here. We see a lot of different percents, so it may be challenging to figure out what we have to do. Let's start by going through and just underlining some key things. So if they have an 80% chance of winning at home, that's one probability. A 60% chance of winning on the road, that is another probability. What is the probability they win any random game in the season? So that is what we're being asked. So what is the probability they win a game? If a random game has a 70% chance of being at home and a 30% chance of being a road game. So we have a couple things to think about. One thing you could do, again, just to help organize, you could create a tree diagram. So I'll just do one briefly and erase it, but just something that you could do. Actually, I'll do it over here. They have two options. They have a home game and a road game. And if they play at home, they have two options from there. They could win or they could lose. Same if they're on the road. They could win or lose. The two branches we're concerned with is winning. So winning at home and winning on the road. So we know the probability of them having a home game, which is 70%. Probability of being a road game is 30%. The probability of winning at home is 80%. And the probability of winning on the road is 60%. So using that idea, using this tree diagram to help kind of organize my information, I should be able to calculate the probability of each outcome. Again, there's two different situations here. Win at home and win on the road. I've already calculated or I've already determined that the probability of them playing at home is 70% or 0.70. And the probability of them winning at home, or winning given that they play a home game, is 80% or 0.80. So now I just need to determine what type of events are these. And looking at these two, they are connected. They're not independent, right? Because I can win given that I'm at home. It's connected. So what's the probability of me winning given that I'm at home? So in this case, the probability of winning at home is going to equal the probability of it being a home game times the probability of me winning given, with that vertical line, that it's a home game. In this case, probability was 0.70 times 0.80, or 70% times 80%. Works out to 0.56, or 56% chance of them winning a home game. Or sorry, winning a game at home. Or 56% chance that that they win a random game if it's at home. For the second opportunity, or the second scenario, winning on the road, we know that the probability of it being a home game, a road game, is 30%, as well as the probability of winning on the road is 0.6, or 60% chance. So if I'm trying to calculate the probability of them winning on the road, again, I've already determined that these are dependent events. Right? The chance of winning on the road is dependent on the fact that they play a road game. So the probability of it being a road game times the probability of them winning, given that it's a road game, I'm going to have 0.30, so 30%, times 60% chance that they win that road game, multiply that together, and I get 18, or 0.18, or 18%. So there's an 18% chance that they win a random game if it's on the road. Again, we're not quite done answering the question, because again, the probability, or the question that's asking, is what is the probability that they win any random game in the season? So we have our two outcomes. They win at home, they win on the road. How do I figure out the probability of these two events? Well, it's here. This is probability of winning at home or winning on the road. Either or works. All right, so this goes back now to mutually exclusive and non-mutually exclusive. Are these two events different? Or are they separate in that sense? And in this case, they are. I can't win at home and win on the road. Right? Those two events are separate. So I'm just going to do the probability of winning at home plus the probability of winning on the road, 0.56 plus 0.18, and combined I get 0.74, or 74%. So there's a 74% chance that they win any random game in the season. Let me just move this stuff around. So this is kind of combining the dependent and independent events, as well as the mutually exclusive and non-mutually exclusive events. So just something to consider when you're going through these questions. Make sure you read them carefully to understand what you're doing. Example 6, the probability of a randomly chosen shopper accepting a sample is 15%. The conditional probability of a customer purchasing the item, given that they try a sample, is 20%. What is the probability that a randomly chosen shopper will purchase the item? So again, I'm going to pause the video, give you a chance to try this one on your own. Again, identify, is it independent or dependent? What are the probabilities of each? And then calculate, using the correct formula, what is the probability that a randomly chosen shopper will purchase the item. So coming back to this question, going through it, we should have underlined and highlighted a couple things. One, the probability of the shopper accepting a sample is 15%. And then based on that, there's a conditional probability that if they accept the sample, there's a 20% chance that they will purchase the item. So what is the probability that a randomly chosen shopper will purchase the item given those two events? Well, we have to multiply them together. They are dependent events because there is a conditional probability there. So given that they accept it, there is a probability that they will purchase it, which was the probability of purchasing given that they accept it. We multiply those two probabilities together, and we should get that there's a 3% chance that they will accept and purchase an item. Going through our last example, a bag contains 2 apples, 1 orange, and 2 peaches. If Sam reaches in for a fruit, then selects another fruit without replacing the first one, what is the probability that Sam chooses 2 peaches? So in this case, again, let's go back and let's underline some of the key things. So there are 2 apples, there's 1 orange, and there are 2 peaches. If Sam reaches in for a fruit, then selects another fruit without replacing the first one. And that's a key thing as well, without replacing the first one, what is the probability that Sam chooses 2 peaches? So we need to think, what type of event is this? Dependent, independent, mutually exclusive, non-mutually exclusive? Well, if we think about it, and if we wanted to rewrite this question, it would be selects 1 peach and selects a second peach. So if we wanted to generalize what this question is asking, we're looking for the probability that he selects 1 peach and selects a second peach. So in this case, the probabilities are changing, or at least the keyword "and" should be a signal that we're looking at independent or dependent. Because he's not replacing the fruit, so he's taking the 1 fruit out and leaving it out. That changes the probability or the outcome of the second fruit. So this is a dependent event. So the probability of 2 peaches is going to equal the probability of selecting 1 peach multiplied by the probability of selecting a second peach. So we'll say second peach, so we'll say second peach given that he's not replacing it, or given that the first event has occurred. So I know it's a little confusing with all the P's. Actually, let's just change those. Let's just change those to fruit. We know the fruit that he's talking about picking is a peach. So the probability of choosing 2 peaches is equal to the probability of choosing 1 peach multiplied the probability of choosing the second peach, given that the first peach was already picked. So in this case, we have to think about what is the probability of selecting 1 peach. So the first pick, what's the probability of selecting 1 peach? Well, I have 2 peaches out of a total of 5 fruits in the bag. Nothing wrong with that. That one's kind of straightforward. It does now change for the second one. So in the second one, we have to consider that the first peach is removed and not replaced. So now we have to think, well, how many peaches are left? Well, there's 1 peach remaining, but how many total pieces of fruit are still in the bag? And in this case, the total number of peaches in the bag, the total number of pieces of fruit in the bag still remaining has now decreased to 4. Because that 1 peach that was removed is not replaced. So there's only 4 fruits left in the bag. One of them is the peach. So this one's a little different because we actually had to calculate that conditional probability. But we can kind of see how we're able to do that by understanding what the question is telling us. So when we go through and we multiply this, 2 times 1 is 2 over 20, reduces to 1 over 10, or 10%. So there's a 10% chance that Sam selects a peach or selects 2 peaches on 2 picks by not replacing the fruit in the first one. So the main things that we should have gotten from this note as we wrap it up. As we wrap this up, the main things, again, looking at independent and dependent events. So we should now be able to recognize or know what to look for when we're given a general probability question. They do look different from mutually exclusive and non-mutually exclusive because we're seeing and in the question was the probability of event A and event B. Given that we have the same type of formula between these 2 events, it is important to figure out, so if we're, what type of events they are. Are they dependent? Does one outcome or one event affect the outcome or probability of another event? Or are they independent where the 2 events do not affect each other? Again, in the general formula, there's not much difference. We're multiplying now. We're multiplying those probabilities. But it is going to be important to recognize if it is a dependent event, because if we do need to calculate the conditional probability, like we had to do in the last question, it is going to be important to know if we need to do that because it should be changing. Right? That second probability should be a little bit different from the first one because the first event has happened and it's affected the probability of the second event. So again, those are the main concepts for this note on dependent and independent events.